Today class, we want to discuss fixed point and floating point representation. I told you I was going to show you that in this class. So what is fixed point and floating point? We have discussed the radix point, and I told you that the radix point is binary point or decimal point in decimal. So since we are dealing with binary, which is what? Bit, we are going to consider the radix point as the what? As the binary point. Now, in the case of a fixed point, the radix point is fixed. And because of that, you can only have a certain finite range of number representation. For example, if we take 4 bits, right? 4 bits. So here you are having 2 raised power 4 equals to what? 16. So you are going to have 16 patterns representation, right? So we are having 0, 0, 0, 0 to what? 1, 1, 1, 1. So this is what? 0 to what? 15. This is how far you can go. If we have something like this, 1, 2, 3, 4, dot 0, 0, 0, 0, which is 1, 1, 1, 1, dot 1, 1, 1, 1. This is equals to what? 0. And this is equals to what? 15.9375. If you do the conversion, I have taught you how to do that. That is, this one is 2, 1 times 2 plus 1 times 2 plus 1 times 2 plus 1 times 2. 1, 2, 3, 4. Plus this side, 1 times 2 plus 1 times 2 plus 1 times 2 plus 1 times 2. Now, having this radix point here, that would be 0, 1, 2, 3. Then on this side will be what? Minus 1, minus 2, minus 3, and then minus 4. If you do the conversion of this is what you are going to get. So it means you are having a fixed range of values. But what if I want to represent 1 million, 30, 60, or 0.0001? I can't have this radix point fixed, right? So that is where the concept of floating point comes in, where we are going to store number with a scaling factor that allows us to represent a huge range of value, right? That is the concept of floating point. So let's demonstrate that for you to see. So if I'm using 4 bits, let's take 4 bits. 4 bits, right? So that would be 2 raised power 4. That would be what? 16. So I'm having 0 to what? 15 pattern. Okay. So it means I have 1, 1, 1, 1. This is equals to what? 15. Now, I want to scale it. I want to be able to represent this number in such a way that I can scale this number to what? To 30. I can scale it to 60. I can scale it to 120. Or I can reduce it to what? 7.5. Half of this. Or reduce it further to 0 point something. So how do I do that? I want the number of bits to still be 4. So I am dealing with what? 16 pattern system, right? So I'm going to have, I demonstrated that for you in the last class. So from 0 to what? To 1, 1, 1, 1, which is what we are seeing. So I want to represent 30, but I don't want to change the number of bits, which is what? Just 4 bits. So floating point has a concept. So the pattern of floating point is what? We are having value equals to mantissa, right? Multiplied by base, raised power what? Exponent. Right? This is the formula. So to have this mantissa, I want to normalize this value. So normalization is simply saying I'm moving the radix point from this fixed point what to this place. So I'm going to, this is represented as 1.111 multiplied by what? 2 raised power 3, since we are using base 2. So this is the same. This is equal to this. So this mantissa is this part, which is still my 4 bits. but I'm having a scaling factor, which is what? Base raised to power exponent. So this is equals to what? 15. What if I want to write, I want to represent 30? This will be what? 1.111 times 2 raised power what? 4. This will give me what? 30. If I do 1.111 times 2 raised power what? 5. This will give me what? 60. That is the meaning of floating point. So this, I'm having this mantissa representing my 4-bit, but I'm changing the value by changing what? The scaling factor. So this is my input into a process that will give me an output. So the output is different bits, different number of bits, but the input is what? 4 bits into the scaling factor, giving me this output. Now, if I do 1.111 times 2 raised power 2, this will give me 7.5. So you can see, you can see the pattern. By just increasing the number of bits or reducing the number of bits, the value is changing. Right? If I am to convert, for example, this one, how is it done? That is saying 1 times 1, 1 times 2 plus 1 times 2 plus 1 times 2 plus 1 times 2. 1, 2, 3, 4, right? Now, where is my radix point? My radix point is here. So this is what? This power 0. You know, the radix points also helps you to know where the exponent 0 will be. So this is what? 0. So from this side will be what? Minus 1, minus 2, and then minus 3. So 2 raised power 0 is 1 times 1. So that is 1 plus 2 raised power 1. This is 0.5, right? Plus this one is 1 over 4. So that will give us 0. Going to 10 will give us 2. 5. So this is 0.25, right? Plus 0. This is 8. So that will give us 0. 10 is what? 1. Going to 20 will give us 2. Going to 40 will give us 5. 0.125. Now, if you add these together, that will be what? 0.5, 0.25, 0.125. That is 5. This is 7. This is 8.1. That is if you add everything together. So this will give you 1.875 multiplied by what? 2 raised power 3. This is 2 raised power 4. So 2 raised power 4 is what? 16. So this will give us 30. Use your calculator. That is what you are going to get. So you can see. Now, it means that if I change this one to maybe 30, you can do the math and see what the value will be. So just by having these 4 bits, I can change my value by changing what? The scaling factor, which is the base times exponent. So that is the meaning of what? Floating point. So this is helping me to move this point. So without this, it means the floating, this point, the decimal point, the binary point, which is the radix point, is fixed. And this can only give me a finite number. But even the floating point also gives you uses a finite input pattern. But it will represent higher range of what? Value, which is the output. So you can see that the concept of the floating point is something that was already discovered in mathematics, which is what? The scientific notation. So where you say 6.02 times 10 raised power 8, writing something like this. But in the case of binary, is 1.111 times 2 raised power 3, right? So it's similar. But there's something I want you to notice. You will notice that in this normalization, the 1 bit at this side of the radix point is always 1. Is always 1. So the computer knows that. So this also helps the computer to save or have one extra bit, because the computer is not going to store this one. Since you know what should be here is always 1, and the computer knows it too. So the computer will only store this part and then this one. So when it's going to populate it on the screen, then the computer will insert this part back. So it helps the computer to save one extra bit, right? So writing your scientific notation in binary format is the concept of what? The floating point that we are looking at. So as you can see, we are building the binary or the bit to what? A meaningful process. So the next class I'm going to teach you two's complement, how to represent negative number in binary. So till we see in the next class, don't forget to give me a thumbs up. And do not forget to subscribe if you have not done so.